Now let's look at the cases where I have an element that's not lying horizontally but tilted at certain angle to the reference axis. Now in this case I can see as shown in this case I have a metal bar that's lying at the angle theta to the horizontal axis of this global frame. Right? Now, just to make the math simpler in solving this problem, I can also define an internal frame, which I have the horizontal axis, which I denote as x bar, parallel to this element, so that the orthogonal axis y, or y bar in this case, is vertical or perpendicular to this element. Now, in equilibrium, right, this thing doesn't move, I can have a force or loading on each of the nodes Fi and Fj, like so. Now that's defined to the global frame. Okay, now be careful that I have made no assumption of this angle between Fi and this bar. So this angle here is not defined and it's not theta. It could be any angle, right? To solve this, we will also notice that I will have an associated deformation Ui along the same direction of Fi and Uj along the same direction of Fj. So we want to work out, right, in the global frame, how do F relate to U? Now, because the forces are not orthogonal, are not parallel to x or y in this case, I will actually have 4 components in total. I will have F I x, F I y, F J x, F J y. That's going to be related to UIX, UIY, UJX, and UJY. Right, this is what we want. So if I project this out to the XY frame, I will have something like this. So let's just do the displacement first. So this is my UI of x, this is my UI of y, and similarly I will have Uj of x, and here I have Uj of y, right? But we actually don't know how to solve this. This is still complicated because this Jx, Jy, or Uix, Uy, they are not, we don't know what's the angle of this, right, with respect to this direction, right? All we know is we can solve a problem if the force and displacement are along the bar. But we can do a similar thing to project this onto the internal frame of this bar. So this Fi, right, in the internal frame, I can also write it as Fi bar and Ui bar. And I can write this as Fj bar, Uj bar, right? No matter which frame I mean, the magnitude or the direction is still pointing that way in this whole blackboard, right? So if I project this onto this internal frame, I will have, in this case, this component UIX bar and UIY bar. And similarly, I will have this component UYX UJX bar and UJY bar, right? So I can actually know in the internal frame, I know how to write the relationship between FIX bar, FIY bar, FJX bar, FJY bar to UIX bar, UIY bar, UJX bar, UJY bar, right? This is what shows in your slide 46, right? Which we know there's a prefactor EA bar over L, right? The first thing to notice is that anything got to do with the Y component should go to 0. Because if the bar is in equilibrium, there shouldn't be any forces that's orthogonal to the bar, right? So let's say if on the two nodes, the Y component goes the same direction, right? Then the whole bar will move like that, right? It will move. If on the two nodes, the force along the Y direction or Y bar direction are opposite to each other, what happens is this thing will rotate, right? So that means in the equilibrium situation, that we are actually not allowed this thing to deform or have any forces along the Y bar directions. So what does that mean? That means basically anything that correlates Y bar to F, Y bar to UY bar goes to 0. So all this matrix element goes to 0, right? And also here, because in the second element it times UY bar, so that also goes to 0, that also goes to 0. That also go to 0 and 0, right? And in the end, what we have left is basically what happened with F bar 1x, Fi bar x with J bar x related to U correlate to UIX bar UJX bar. And you know from the previous lecture, this thing has a diagonal matrix element with diagonal matrix that look like this: +1, -1, -1, +1. Right? So you put this back into this, we get 1, -1, -1, 1. Okay? So now that's all good for everything with this internal frame. Okay, internal frame, this is all good. What we're going to do next is to figure out how we can change everything that's in the internal frame coordinate to the global frame coordinate. So how does, for example, UIX or UJ, how does UI of X correlated to anything got to do with a bar on top, right? How do we work out this from this or vice versa. Now to look at that, we see that, okay, I have this u1x that is pointing to this direction, and I have u1, so this is u1x, which is the same as in magnitude uix without the bar. So with bar, without bar is the same. Now I have this u1x and u1y in this global frame. But how do they look like in this internal frame? Well, they look like this. They look like u1y, uiy, and uix, right? And they should all add up to this thing called uix bar, right? So how do I work out, how will I get from this uix and uiy to this x bar? So this is uix bar, right? And this is angle theta. What you can see is that both of these two displacements will have some component along this direction, right? Because this direction is not orthogonal to either one of these two. So what you can do is project each of these onto this axis. So if I project u1x onto this x bar axis, so I will have this uix bar, and I have this uix. I need to project this onto this x bar direction, which is basically cos theta, right? This is your vector algebra. And similarly, I can project this uiy onto this x bar axis. That gives me uiy times sine theta, right? Now basically you can do the similar thing for all the displacement on each node. So if you write that down, we will get something like this: uiy equal to u minus uix times sine theta plus uiy times cos theta, ujx equal to ujx cos theta plus ujy times sine theta, u bar jy or equal to minus ujx sine theta plus ujy cos theta, right? And similar apply to the forces, right? So if you put all these together, what you can find out is you will be able to write the relationship of uxi bar u. Let's just put this in the same order: uix bar, uiy bar, ujx bar, and ujy bar related to uix, uiy, ujx, and ujy as what? In this case, this is cos theta sin theta 0 0 minus sin theta cos theta 0 and 0 0 0 cos theta and sin theta 0 0 minus sin theta and cos theta, right? And similarly, we can write same thing for f(ix), f(iy) with bar, fjx bar, and fjy bar. And this is basically the same thing, fix, fiy, fjx, fjy, right? And to simplify this notation a little bit, I can define this as a orientation matrix. So let's just call this thing T over E. That shows what? That shows U in the bar frame. U bar is equal to T of E times U. Right? U bar equal T of E times U. And similarly, this is also T of E, so I can say F bar equal to T of E times F. Alright? Now, because we know, what do we know? We know F. We know in the internal frame, right? F bar equal to K bar times U bar. So what is this K bar? K bar is basically this guy. So in this case, we have this as our K bar, right? So in the global frame, F equal to K times U, and this K can be related to the internal K bar as T E transpose times this internal K bar times T of E. So this is how you will get out the stiffness matrix in the global frame from those in the internal frame. And if you substitute this TE into this equation here, what we'll get out is the final K matrix, which is E over A, EA over L times cos square theta sin theta cos theta minus cos square theta minus sine theta cos theta, sine theta cos theta, sine square theta minus sine theta cos theta minus sine square theta minus cos square theta minus sine theta cos theta cos square theta sine theta cos theta minus sine theta cos theta minus sine square theta sine theta cos theta and sine square theta. Right, this thing looks a little bit complicated, right? But in a real application, this whole thing, right, will be given to you, which you can just plug in the value of theta to work out what will the stiffness matrix be and how it can work out the deformation from the value of the external forces. But the key idea here is to understand, right? There are lots of complicated math in this, but the most important thing to take home from this exercise is that I have some loading, right? That's on an arbitrary direction, which we don't know what this phi angle is, but I can work it out based on the component that is orthogonal or parallel to the global frame and the other component that is parallel to the internal frame. I can set up a relationship between this red component and this blue component from which they allow me to work out the stiffness matrix of the whole thing. So that's the basic idea behind this exercise.